So this is the introduction section to chapter 9. And really it's just kind of laying the framework for what we're going to be doing in this chapter. And the idea is that we are going to be having systems of differential equations. Now your book gave the following example. They gave an example from a previous chapter. Dx dt is negative 4x plus 2y, and dy dt is 4x minus 4y. And what this was an example from a previous chapter where you had two different tanks of salt water, but they were kind of connected to each other, and you could have, water flowing back and forth and going out, and you had to try to take into account all of that here. And the problem is that since you had two different containers, you had two different amounts of salt at any given time, one in the left and one in the right, which meant you had two different unknown variables, x and y. And so that means we don't just have a single differential equation like we're used to. We have two differential equations, and furthermore, they're interconnected, right? If this first differential equation, if this only had x in it, then I could solve for x, and then I could plug in the bottom one. Similarly, if this bottom one only had y, I could solve for y, and then plug it in the first one. But I don't have either one of those. I have this interconnectivity between the two variables. And that means that all the techniques we've learned before chapter 9 are going to be completely insufficient to solve this problem. But what we can do is we can take this problem and we can rewrite it in a matrix format. And this is not a minus. So we can rewrite this in a matrix format, and it's going to turn out that we can then use our matrix knowledge from the linear algebra portion of this class in order to get the answer to this differential equation. So on exam 1, when we did differential equations, we absolutely could not handle anything with two variables. Couldn't be done. But now we're going to learn how we handle this, and the way we're going to do that is going to involve stuff from matrices that we learned in the second part of the class. And just to kind of show you that this is actually a more general technique than we might think, what if I had, say, a third degree differential equation? Let's say 3y double prime plus 5y prime minus 9y equal to 0, let's say. Now, this is a third order constant coefficient, and you could solve this like we did in the past. However, what we can do instead is we can change this by saying that my new variable y1 is the original function y, and my new variable y2 is the derivative of the unknown function, and my new variable y3 is the second derivative. And if that's the case, then what happens if I take the derivative of each one of these? Then y1 prime would be y prime, which is the same as y2, and y2 prime is the same as y double prime, which is y3, and y3 prime is y triple prime, and that, if you solve for it up here, is minus 3y double prime minus 5y prime plus 9y, which is the same as saying 9y1 minus 5y2 minus 3y3. And once you've done this, you can rewrite this in the following fashion: y1, y2, y3 prime, and it's going to be 1y2, 1y3, and 9, negative 5, negative 3. Now, we're not really going to solve problems that look like this. We're going to only solve ones that are given in matrix format in this class already. And we're only going to solve ones that already have x and y in them. But I just wanted to show you a quick example of how you can take a higher order differential equation, so this is a third order here, and you can turn it into now only a first order equation as long as you have a system of equations. And if you had a 10th order equation, you don't have to solve 10th order, all that craziness. What you do is turn it into a single first order system of equations, where it's going to be a 10 by 10 matrix, which is certainly not pleasant. But again, matrices are really good for calculators and computers. And so this is, in fact, a better way to solve those higher order differential equations. Now, when I'm dealing with this here, we're going to have a little bit of terminology here. This part right here that's going in front of the right-hand side variable part, we're going to call that the coefficient matrix. And it is entirely possible that those coefficients involve your x or your t or something like that. It's entirely possible that those were going to involve your variable. For example, if this up here had been a 2ty, that's a really bad color, so I apologize. Maybe this would be better. If this had been a 2ty, you'd have a 2t in the matrix, and again, there's nothing wrong with that. There are still ways to solve it, but for our class, we will not be dealing with that. We will only be dealing with coefficient matrices that are all going to be constants, for us at least. But I just wanted to let you know that it's entirely possible that you could have something like that where they are not constants. So this section, again, it's just the introduction, just to lay the groundwork for what we're doing in this chapter. And then later we're going to see what the actual mechanism is to solve these problems.